Okay, that looks good. Okay, so our next speaker is Jason Parker, and his title, as you can see, is Presentations and Algebraic Colimits of Enriched Monads.
Great. So thanks for the invitation and for the introduction. So I'm Jason Parker, and this is a joint work with Rory, Lucish, and Wright. So the title, as Susan said, is Presentations and Algebraic Colimits of Enriched Monads. Okay, so just to introduce this material, oops, I have to click, there we go, okay. So basically, signatures and presentations for monads and theories in enriched universal algebra have been mainly studied in the past in the context of locally representable enriched categories. So for example, we have some papers that study these phenomena, at least in part. We have, say, this paper of Kelly and Power from '93 called Junctions whose co-units are co-equalizers and presentations of finitary enriched monads. We have basically, it's a successor of it by Lack from I think 6 years later, called On the Monadicity of Finitary Monads. We have actually also a recent paper by Burke and Garner called Monads and Theories. But in this talk, we'll discuss basically recent work with Rory on developing a framework for studying these phenomena that subsumes a much larger class of enriched categories, namely the locally bounded enriched categories that Rory spoke about just now, and also, for example, the symmetric monodal closed pi categories of this paper by Bourseau and Day called Universal Algebra in a Closed Category. Okay, so just to set the stage, so a subcategory of arities in a V category C is just a full and dense sub-V category. So nothing too complex there. In this talk, but not in general, we'll assume J to be small, but you can take J to be large. In fact, there is a canonical subcategory of arities where you just take J to be C itself, the entire V category. But in this talk, J will be assumed small. So a subcategory of arities, we'll say, is eleutheric in the sense of Rory's paper called, I think, Enriched Algebraic Theories and Monads for a System of Arities. So if any V functor f from J to C has a left conextension along the subcategory of arities J, and moreover, it's preserved by each of the representable V functors for each object in the subcategory of arities. So this entails in particular that the ordinary category of V functors from J to C is equivalent to the category of so-called J-ary V endofunctors of C, which are by definition V endofunctors H of C that preserve left conextensions along J. So soon we'll see some concrete examples of eleutheric subcategories of arities and their corresponding J-ary endofunctors. But before that, I'll just give some more kind of background. So if J is a subcategory of arities, then we'll write monad subscript J of C for the ordinary category of the J-ary V monads on C. So the V monads whose underlying endofunctor is J-ary, so preserves left conextensions along J. Now, in particular, if C is just V regarded as a V category enriched over itself, and J from J to V is an eleutheric system of arities, which means that J contains the unit object I and is closed under the monoidal product, then actually Rory proved in the paper I mentioned before that the category of J-ary monads on V is equivalent to the category of so-called J theories as he defined them in that paper. Okay, yeah, so now, again, before getting examples, I'll discuss some assumptions that we'll be imposing on our subcategories of arities to obtain the main results that I will discuss. Just keeping my own time. Okay, so, right, so Rory basically talked about enriched factorization systems and kind of compatibility of them. So I'll just basically review what he said with some kind of additional terminology. Right, so we basically invented this kind of term called factogory. So because we got tired of saying category with a factorization system so many times. So basically a symmetric monadal closed factogory is a symmetric monadal closed category V, just equipped with an enriched factorization system. Now, if C is a V category enriched over a symmetric monadal closed factogory V, then an enriched factorization system, which we write EC MC on C, so we just subscript E and M with the name of the given V category. So this is compatible with EM if all of the representable V functors for C preserve the right class. So they send M morphisms in C to M morphisms in V. And so now if V is a symmetric monadal closed factogory, we say that a V factogory by definition is a V category C equipped with an enriched factorization system that is compatible with the given one on V in the sense in the previous point. And then we'll say that a V factogory is co-complete by definition if the underlying V category is co-complete, and moreover, the V category C has arbitrary co-intersections of morphisms in the left class. So this means, as Rory basically explained, that any possibly even large family or class of morphisms in the left class with the same domain has a colimit, also called a co-intersection. Okay, so these are factogories. Okay, so now I'll discuss kind of a main or idea that Rory basically also discussed, boundedness. So let alpha be a regular cardinal, and let C and D be V factogories with conical or just alpha filtered colimits. So that means that the underlying ordinary categories have alpha filtered colimits, which are preserved by each of the representable V functors to V. So we say that a V functor F from C to D is alpha bounded. Now this is a somewhat technical definition, but I'll kind of give more intuition after. But so if we have any alpha filter diagram in C, or more precisely in its underlying ordinary category, with colimit colim D, and any MC cocone on D, which is just a cocone on this diagram, where each of the morphisms in the cocone happens to lie in the right class M of the factogory C, then if the induced morphism M bar from colim D to C lies in the left class of E, then sort of the corresponding induced morphism in D lies in the left class of D. So basically, yeah, so I'll just put this, yeah, so I'll basically, so essentially this is kind of like a factorization system theoretic variant of the notion of preserving alpha filtered colimits. And so I'll come back to that point in a second. So F is bounded just if F is alpha bounded for some alpha. And if we have an object C in the given V factogory C, then we say that C is alpha bounded if its representable V functor is alpha bounded. So now if all of the involved factorization systems happen to be sort of the trivial one, iso all, where the left class is the isomorphisms and the right class is just all morphisms, then it's easy to see that F is alpha bounded if and only if F preserves alpha filtered colimits. So basically this notion of alpha boundedness is, as I mentioned, kind of a factorization system theoretic variant of the notion of preserving alpha filtered colimits. Okay. Right, so now if we have a subcategory of arities in the V factogory, C, then J is alpha bounded by definition if each object in the subcategory of arities is itself alpha bounded. Okay, so one key result that we prove, which essentially enables all of our results, is that if J is an alpha bounded subcategory of arities in a co-complete V factorial C, then any J ary endofunctor of C is itself alpha bounded. And in fact, more generally, any left con extension along J, which is an endofunctor of C, is alpha bounded. Okay. Okay, so now, before finally giving some examples, I'll just state the blanket assumptions that we'll be imposing on the given data that will enable all of our results. Right, so all of our results that I'll be discussing in forthcoming slides, they hold for any subcategory of arities in a V category C, satisfying the following assumptions. So first, just V has to be complete and co-complete, symmetric, monadal closed factogory. The factogory assumption is not very strong because, as I kind of hinted at, you can just take iso all in many but not all examples. So that's not a super strong condition or anything. So C is a co-complete and co-tensored V factogory, such that either the factorization system on it is proper, meaning that the left class is contained in the epis and the right class in the monos, or C is eco-well powered. And so if the factorization system happens to be iso all, then that second property is trivially satisfied because any category is iso co-well powered. And yeah, so eco-well powered just means that any given object has just a set up to isomorphism of E quotients. So maps, so E maps going out of the object. Okay. And finally, the subcategory of arities J has to be bounded in the sense defined and eleutheric. Okay, so we have actually a lot of examples that do satisfy these assumptions. So now I'll finally give some examples. So if we have a locally alpha presentable V category C over locally alpha presentable closed category V, then the subcategory of arities on the alpha presentable objects satisfies our assumptions. So in this example, the J-ary endofunctors are just those that preserve alpha filtered colimits. This is also known as having rank alpha or being alpha accessible in the terminology of certain authors. And the J-ary monads correspond to the enriched Levere theories of this paper by Power and Nishizawa, where alpha is Aleph naught. The subcategory of arities consisting of certain phi presentable objects in a locally phi presentable V category for a class of weights phi satisfying axiom A from this paper, Notions of Levere Theory by Lack and Rositzky, in a locally bounded and eco-well powered closed category V. So we showed this so Rory and I proved in current work that if V is locally bounded and eco-well powered, then so is any locally phi presentable V category. And so that entails that this subcategory of arities is bounded by a result that I'll discuss later. Yeah, and then here the J-ary endofunctors are those that preserve so-called phi flat colimits. And the J-ary monads could correspond to the Levere phi theories of this same paper. So as an example of this the subcategory of arities of D presentable objects in a locally D presentable V category over a locally D presentable closed category V for a sound doctrine D satisfy our assumptions, where a sound doctrine is meant in the sense of this paper, a classification of accessible categories by Adamic and Bourseau and a few other authors, I believe. So here the J-ary endofunctors are those that preserve conical D-filtered colimits. So here's kind of a somewhat simple example. If you take any complete and co-complete symmetric monadal closed factogory V, the subcategory of arities consisting of just the unit object satisfies our assumptions. And here the J-array endofunctors are those of the form X tensor blank for just an object X of V. And the J-array monads correspond to monoids in the monodal category V. Okay, so if you take any symmetric monodal closed pi category V in the sense of this Bourseau-Day paper called Universal Algebraic Closed Category, then you can take the subcategory of arities on the finite copowers of the unit object, and that will satisfy our assumptions. So here the J-array endofunctors are those that preserve so-called NV flat colimits, which includes sifted colimits. And the J-array monads correspond to the Bourseau-Day enriched finite power theories in this paper. Okay, finally, kind of an example that ties back to Rory's talk is that any eleutherix subcategory of arities whatsoever in a locally bounded V category C over a locally bounded closed category V satisfies our assumptions. So this gives kind of tons of examples. Okay. So now I'll get to the main results finally. So we have a subcategory of arities J, then a J signature in C is just a functor from the objects of J to C. So it's just an ob-J indexed family of objects of the V category C. And we then get a canonical forgetful functor, which I'll write as V, from the category of J-array endofunctors on C to the category of J signatures in C. Just sends any J-array endofunctor to the signature that you get by applying the endofunctor to each object of J. So one thing we proved is that this forgetful functor is monadic, so it has a left adjoint in particular. And so the free J-array endofunctor on a signature sigma is the polynomial endofunctor H sigma, which sends any object X of C to the coproduct over J in the subcategory of arities of this internal HOM C of JX tensor sigma J. That's the object corresponding to J in the signature. Okay, so there's also a forgetful functor from J-array monads to J-array endofunctors, which we want to show has a left adjoint, and follows that it will be monadic. And also we want to show that the composite forgetful functor from, or U, from J-array monads on C to J signatures is also monadic. So there are some precursors to this results in the literature. So Kelly and Power showed in that paper that W has a left adjoint in this specific example when J is the subcategory of alpha presentable objects in a locally alpha presentable V category over a locally alpha presentable base V. And then Lack took this further and showed in the paper I mentioned that this U is monadic in this context. Borkin and Garner recently showed that if C is locally presentable, as is V, then this similar but not the same functor is monadic. So here we have the category of so-called J nervous monads on C to J signatures. Okay, so what we will do, or what we have done, is prove this theorem. So if H is any J-array endofunctor on C, then the forgetful V functor from H algebras to C has a left adjoint under our assumptions, and the induced V monad G after F is an algebraically free V monad on H, in the sense that this monad has the same, or has an isomorphic V category of algebras. And moreover, we showed that this monad is in fact J-array. So therefore, this forgetful functor from J-array monads on C to J-array endofunctors has a left adjoint, and it follows that it is monadic. So therefore, in particular, any J signature has a free J-array monad. And also we show that the V category of algebras for this monad is isomorphic to this V category of sigma algebras, which has a more kind of concrete description. Okay, so now I'll go on to presentations of monads. So let J be a subcategory of arities, again satisfying all of our assumptions. A J presentation is a pair of J signature morphisms, alpha beta, from a J signature gamma to the underlying signature of the free J array monad T sigma on the signature sigma. So one can think of gamma as the signature of equations, and alpha and beta send sort of any equation in gamma to its respective terms, so to speak. So now we want to show that any presentation sort of generates a J array monad TP, which means that we want the induced diagram of monads to have a coequalizer in J array monads, which is also preserved by the semantics functor alg from J array monads to vcat over C op, which is it's a contrarian functor that sends any J array monad to the forgetful V functor from its V category of algebras. Right, so if we have a small diagram of J array monads in C, M, or write G, M from M alg to C for the limit of the induced functor alg after M op. So basically this is kind of the limit of the V categories of algebras of the monads in the diagram. So what we showed is that, so also a colimit in this category of J array monads is algebraic by definition if it's preserved by this semantics functor alg. So what we proved is that under our assumptions, if we have such a small diagram of J array monads, then this sort of limit forgetful functor has a left adjoint, and the resulting V monad is an algebraic colimit of the diagram, which is actually also J array. So therefore, this entails that the category of J array monads on C has small algebraic colimits. And this entails that any presentation presents a J array monad. And also we show that if TP is the J array monad presented by a presentation P, then its V category of algebras is isomorphic to the V category of P algebras, which is a kind of a more concrete V category. Okay, so using this theorem from Lack's paper that I mentioned, we also showed that under our assumptions, the forgetful functor U from J array monads to J signatures is monadic. And as a particular consequence, this entails that any J array monad on C has a presentation. So any presentation presents a J array monad, and any J array monad has a presentation. Okay, so now I will connect this to locally bounded V categories. I'm close to time, but okay. So we prove that if C is a locally bounded V category over a locally bounded closed category V, then any small subcategory of arities in C is bounded. So thus, all of our results hold for any Eleutherich subcategory of arities in any locally bounded V category C over a locally bounded base V. So I'll just give some examples of that. So far we have the following examples of Eleutherich subcategories of arities in locally bounded V categories. So we have a locally alpha presentable V category over a locally alpha presentable V, then in particular, it's true that C is locally alpha bounded, and so is V. And then we have this, as previously mentioned, Eleutherich subcategory of arities on the alpha presentable objects. Similarly, we have for any sound doctrine D, the subcategory of arities on D presentable objects in a locally D presentable V category over a locally D presentable base V will be Eleutherich, and these given V categories will be locally bounded as well. So we have any, but in particular, a locally bounded closed category V. And the subcategory of arities on just the unit object is eleutheric and also bounded. If we have any locally bounded or just any arbitrary symmetric monadoclosed pi category, so which includes, for example, any complete and co-complete Cartesian closed category, this subcategory of arities on the finite copowers of the unit object is eleutheric. And lastly, so as I mentioned before, Rory and I have proved that if V is locally bounded and eco-well powered, and we have a class of weights phi satisfying axiom A from the Lack-Rosiczky paper Notions of Lavoie Theory, then any locally phi presentable V category is locally bounded. And hence this subcategory of arities, which we saw before is eleutheric, is also bounded as long as it's small. Okay, so I'll start wrapping up. Yeah, so basically we have developed a framework for studying signatures and presentations for enriched J-array monads for subcategories of arities J. That includes locally bounded enriched categories and also the pi categories of Bursa and Day. So more specifically, we've shown that free J-array monads and presentations for these monads can be obtained for any bounded and eleutheric subcategory of arities in any complete, co-complete, and co-tensored V factogory C. And in particular, our results apply to any eleutheric subcategory of arities in any locally bounded V category over a locally bounded closed category V. So I believe that is the conclusion. Yes, so thank you very much.
Okay, thank you, Jason.
Thank you.
Unmute and clap.
Oh, sorry, I think I'll just go back to full screen. Yeah, okay.
Okay. We have time for maybe one quick question. We have 2 minutes till the start of Matthias's talk. Okay, well, let's thank Jason again. If there are any questions, you can ask them in the forum.
Yep,
Okay.
definitely. Thank you.
So we can unshare so Matthias can. Thank you.